So we're doing problem 2 from the weekly homework. There we are. And once you've got your picture set up, you know the distances from Q1 and Q2 to Q, and the distance between Q1 and Q2, which become important when you want to figure out first everything on your pictorial diagram. So we want to get these three angles before we do anything else. And to do that, in the case when you don't have a right triangle and you only have three sides, then you can find any of the angles by using law of cosines. We're going to find this big angle first. And so to do that, we use law of cosines, which is c squared equals a squared plus b squared minus 2ab cosine the angle in between them, a and b, which is that big angle. And so you can see I've moved from centimeters to meters. I plugged in my c, my a, my b, my a, my b, cosine of theta. You're going to solve this step by step. Don't try to plug everything in your calculator at once. In fact, first you need to square this. Write it down on the next line. Square this plus this minus da 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 da. And once you work it down, you're going to get it to where you have theta equals the inverse cosine of whatever value you have. And then you end up with theta is 97.1. Since we know that these two sides are the same, we know the angles opposite have to be the same. So since we know 180 degrees total in any triangle, if I subtract the angle I found, I know the two angles have to add up to the remaining 82.9. So I divide that by 2, I get about 41.5. And so we can put that in here. These are 41.5, 41.5, 97.1. Let's just make that 97 so it actually adds up. Okay. So next thing we're going to do is we're going to think about the problem that we have at hand. So if we're given an acceleration, we know that the net force and the acceleration are in the same direction. So what we need is a force diagram for Q, because the other thing we got to figure out is what are these signs? I've already marked them positive and negative. But the way you figure that out is you need on your force diagram the force exerted by Q1 on Q plus the force exerted on Q2 on Q has to add up vectorially so that they're in the same direction as the acceleration. The only ones that work are if Fe Q2 on Q is repelling big Q, which makes Q2 negative. All right, it has to be going in this direction so that there's a component, the y component is in the same direction as the acceleration. And that would be the y component going this direction. The next one, Fe Q1 on Q, has to be attracting, which makes Q1 positive. All right, I have to have my force of Q1 on Q in this direction so that my y component is in the same direction as the acceleration, or the same direction as the net force, right? Which are the same direction. So I transferred Q to from nanocoulombs or microcoulombs to coulombs, so that gives me 1.75 times 10 to the negative 6th. I know the acceleration magnitude is 324 meters per second, and I know the mass of Q. So since we are given acceleration, we want to start with second law. We know the net force has to equal mass times acceleration. So I can solve for that net force by plugging in mass times acceleration. It gives me 1.62 newtons. And I know that the net force is the sum of the two forces on my force diagram, FeQ2 on Q plus FeQ1 on Q, which gives me this statement. And this tells me how to draw my triangle in two dimensions. Second law tells you how to draw the triangle, right? The net force, in this case, we know it's upwards because we were given the direction of acceleration. So this tells us how to draw our triangle, and it tells us the lengths of one of our sides. So this is the net force. These are the two forces I had to get the net force. And I did that here, right? So notice you can move these vectors anywhere in space, but rules of vector addition say I have to add them head to tail. So these two are added head to tail, and my net force, the resultant, is draw tail to tail, head to head. And so this 1.62 newtons, which is the magnitude of the net force, I know is the length of this triangle, right? The reason I went and did my angles when I had the dimensions and distance is because these angles are going to be the exact same angles here because all the vectors are in the same directions as these displacements. So I've got my triangle set up and I've got 3 angles and 1 side. Law of cosines would work, but the easier one, when you have 3 angles and 1 side, use law of sines. It's easier, it's quicker. So law of sines set up, I know it's side A over the sine of the angle opposite side A equals side B over sine of the angle opposite side B equals side C over the sine of the angle opposite side C. And so in this case, I'm going to have this side over this angle is equal to this side over this angle. Because I only need to solve for one of these electrical forces, because my goal is to find the magnitude of Q, which I know is in the electrical force due to Coulomb's law. And I know Q1 magnitude is equal to Q2 magnitude. So I only need to solve for one. So I set it up with side C over the angle opposite side C. So 1.62 newtons over sine of 97.1, which comes from here. Side A over angle sine of the angle opposite, equals the side I'm looking for, FEQ1 on Q, over the sine of the angle opposite, which is this side and this angle. And then I do a little good old arithmetic, multiply both sides by sine of 41.5, and this is going to be a number equal to this electrical force. So my next step is then to write in the variables, turn this into, using Coulomb's law, I can write the variables that I know, and it'll leave me with the one I don't know. So then your formula looks like this, right? So the electrical force is equal to KQ1 times Q over D squared. And then this is the remaining side that you probably have, you can solve as a number. So I plug in my K, my big Q, my Q1 I'm solving for, and the distance between Q1 and big Q, which is 0.03, and I'm squaring the distance because that's Coulomb's law, right? So rearranging again, we'll get all of your knowns on one side and Q1 on the other, and I solve this value for the magnitude of Q1. All right, this is homework 2, problem number 2. We start off with our pictorial diagram. And so we have our 3 charges, Q1, Q2, and Q3, and the distance between them. We're given 0.04 and 0.03. To solve for this third side of 0.05, since it's a right triangle, we just use Pythagorean theorem, a squared plus b squared equals c squared, and that tells us side C, the hypotenuse, is 0.05 meters, which I've labeled there. The next thing we do on our pictorial diagram is to find the angles. And to do that, we use, for a 90-degree angle, we can use SOHCAHTOA. In this case, we want to find this angle, then we're going to use opposite over adjacent. So tangent of that angle theta is going to be 0.03 over 0.04, because I'm doing the opposite side, 0.03, over the adjacent side, 0.04. And that tells me that angle is 36.9 degrees. It is perfectly all right to solve for this side. You'll of course get slightly different answer for this angle, but all your answers will remain consistent with that. So we're asked to find the X and Y components of force acting on Q3. So if we want to talk about force, of course, our first step is to do a force diagram. It's Q3 that we're interested in. And so we see since Q3 is positive and Q1 is positive, then there's going to be a repulsion. Electrical force of Q1 on Q3 is going to be in that direction. And then since Q2 is negative and Q1 is positive, we're going to have attraction. And so the electrical force of 2 on 3 is straight down. Okay. The next thing we need to do, since this asks us specifically for X and Y components, is we need to break up any vectors not in the X or Y direction into its X and Y components. So f of e 2 on 3 is all Y, so it's fine. It's our f of e 1 on 3 that we're going to need to make into an X and Y component. So I follow my rules of vector addition, and X and Y should add head tail to equal the total fe 1 on 3, and then I'll label those. This one's in the Y direction, 1 on 3, and this one's in the X direction. Okay, so now I know I'm dealing with these three vectors, f of e in the y direction, which points up, f of e in the x direction points to the right, and f of e 2 on 3, which points down. Notice I keep track of which way is positive and negative, because in the y direction, f of e y 1 on 3 is up, and f of e 2 on 3 is down. So those are going to act against each other. So it asks us to find the x and y components of the force on Q3. And so if I want to find the x component, I need the sum of the forces of all the forces that are just in the x direction, and that's only one force. It's f of e x 1 on 3. Notice you get that from here. The only one in the x direction is this f of e x 1 on 3, so that's going to be my x component I need to solve for. On your force diagram, something that you could have done originally is, since you know these two are just strictly Coulomb's law, you can go ahead and solve for them. So I did that here. Here's f of e 1 on 3. kq1 q3 over d squared. Here's the values you plug in, and that's the answer you should get. Right, and notice I've converted everything to coulombs. So nanocoulombs is just times 10 to the negative 9th of whatever you're given to get it into coulombs. Right, and then that's my distance between q1 and q3 is 0.05. So that's what you get for f of e 1 on 3, for f of e 2 on 3, similar, except I'm using kq2, kq3 in the distance between 2 and 3, which is 0.03 squared. Again, I've converted into coulombs, and that's my answer. So I put this to the side, right? And then we go back to, if I'm solving for the x component, I want the total sum of forces in the x direction, which is only f of e x 1 on 3. In order to solve for that, I'm going to have to use trig, because I know this side, and I found this angle. Remember, they're in the same directions as these displacements, so this angle is this angle. So now I've got, if I want to solve for f of e x on 3, I've got an adjacent side and the hypotenuse. So I use cosine of 36.9 degrees equals that side I'm looking for, f of e in the x direction on 1 on 3, over the hypotenuse f of e 1 on 3. And so here, I've just plugged in those values. If I multiply the value of f of e 1 on 3, which is 1.08 times 10 to the negative 4th, I'll move this to this side and isolate f of e x. And that looks like that. And then I just solve for this value, and now I know that my x component is equal to 8.64 times 10 to the negative 5th in magnitude, and I know its direction is in the positive to the right. So my x component's done. My y is a little more complicated because I have more than one vector in the y direction. So if I look in the y direction, I have f of e y 1 on 3 and f of e 2 on 3. So all right, I want the sum of forces in the y direction, so I have to add those two vectors. I know this vector already I solved for, so I need to solve first for this one before I can plug in. So again, similarly to finding in the x direction, this time I want this guy, y direction, f of e y 1 on 3, which is opposite the angle. And I know the hypotenuse, so I can use sine of 36.9 degrees equals f of e y 1 on 3 over f of e 1 on 3, which looks like this. Sine of 36.9 degrees equals f of e y 1 on 3 over f of e 2 on 3. Again, I'm going to plug in this value and multiply it across, which looks like this. And then solve for this side, and I find that the y component of the electrical force of Q1 on Q3 is equal to 6.48 times 10 to the negative 5th. Clean that up. Okay. So now I've got this value and this value. So remember, I'm finding the y component, so I need all of the forces in the y direction. So if I'm adding the y component of electrical force of 1 on 3 plus the electrical force of 2 on 3, I have to account for their directions now. So when I put in those values, I do so. Sum of force in the y direction then is 6.48 times 10 to the negative 5th minus, since f of the electrical force of 2 on 3 is downward, 1.2 times 10 to the negative 4th, and that total becomes negative 5.52 times 10 to the negative 5th, which tells me the y component is downward, which is consistent with my reference frame that downward is negative. So if done correctly, your math tells you the direction.